We're going to start with addition, because that's where most people start in our curriculums in school. But understand that with Mortensen mathematics, all you need is the ability to count to 9, identify a rectangle, and understand whether something is same or different or not. And we can start anywhere, in problem solving, subtraction, multiplication, division, or addition. It doesn't matter. But we play games, many games. One of the games is called having a party. And we can start, of course, with the lower numbers, but because of time constraints, we're going to start with 9. So of course we've been playing with numbers, and we've been playing building 5s and 6s and 7s, and now we're going to play building 9s. So here is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I want to build a 9, I need to start off with something here for the children, and we're going to say this is an 8. What does 8 need to be a 9? Or if 9 was having a party and 8 wanted to go, who would he have to take? Well, it's visually obvious.
What Ben needs is one of me, a green unit, one of me, and that makes 10. I'm the green guy. One unit, that's what you see. Everyone else, every unit and block is made of me. The other blocks can make me a 10. 10 of me or help adding up with them. I do it all when the others fall. I make it happen and the count starts rapping. Yeah, I rap, I dance, I'm always up, counting snaps. I'm where counting starts. I'm how it happens. So I'm always a part of everything and all. If it comes to math, 10s look big, I just look small. So when everyone wants to be a 10, it's with me they must begin. When you learn math, you start to
And if 7 wanted to go, and little kids enjoy this. If 7 wanted to go, well, have to bring a 2. And of course, if 6 wants to go, 9's party needs a 3. Now all this is, numbers are made up of other numbers. We can build 8s and 7s and 6s. We can build 5s and 4s. 4s are pretty boring to build. We can build 3s, which are really boring. We can build 2s, which are really boring, because the only way you can build a 2 is with 2 1s.
Hey, yo, oh, wait a minute. Green guys are never boring. Using 2 to make a 2. That's exciting. That is never boring.
But for little children, when they're first discovering this, it's a ton of fun. And we play many other games to bring this concept home. Now, 8 needs a 1, 7 needs a 2, 6 needs a 3, and the last one, of course, 5 needs a 4. Now the reason why we spend so much time on this is because it is crucially important that children understand that numbers are made up of other numbers. Alright, now we spend a lot of time and emphasis on building 10s, since of course it's base 10 mathematics that we're teaching. This is a 10. Now, what does 9 need to be a 10?
What Ben needs is one of me, a green unit.
And of course, all the other numbers want to be 10s. 9 needs a 1 to be 10. And of course, 8 needs a 2. And again, it's visually obvious to the child. And you'll notice we're not using any symbols on this board. We're just playing with blocks and using verbal and kinesthetic skills to build 10s. And later on, we can put the symbols in. So 9 needs a 1, 8 needs a 2, 7 needs a 3, 6 needs a 4, and 5 needs a twin if he wants to be 10, or if she wants to be 10. And all we've done here is build with blocks and have a good time. Now here, all we're doing is showing you the blocks. We have lots of games where we build towers, and we can stand them up and make skyscrapers where they use their motor skills, their finer motor skills, to place the blocks on top of each other and basically understand that we can build numbers out of other numbers, and in this case we're building tens, and we need to have these concepts understood and readily available to the child's mind, so that later on when we teach subtraction, and you'll see other things like problem solving and so forth, that they have no problem understanding what they need to do, and they don't have to count on their fingers. Subtraction. In more than mathematics, we like to put the children in a situation where they cannot fail. If they cannot fail, they'll succeed. Now here we have 19 take away 5. And we've played games where we understand that numbers are made up of other numbers. And remember, we were having a party with 9. And if 9 had a party and 5 wanted to go, who would he have to bring? Well, let's see here. There's 5. If I am going to build a 9 with a 5, well, you can see what's going to fit there. A 4. So if I take this 5 away from 9, there's 4 left. And it's very simple. 14. Now, it gets better. Now here's a slightly more complex problem. 15 take away 8. Now I've actually seen students do this. And then they count backwards. All right, let's take a look at it a slightly different way. If I have 15 and I want to take away 8, do I have enough? Can I take this 8 out of this 15? Out of this 5? Well, I can't. What do? I take it out of this 10. Now we know we played want to be a 10. What does 8 need to be a 10? It needs 2. So you can see a 2 would fit right there easily. That's it. Take away 8 from the 10, and I have 7. So what I did in my mind is add 2 to 5 to get 7. We can always hit rewind. We're going to do a couple more problems quickly. Okay, a slightly more complex subtraction problem. 23 take away 7. Again, all I'm going to do is add, because you'd much rather add small numbers than subtract. So, do I have enough? The first question. Do I have enough? Well, I don't have enough. I can't take this 7 out of that 3. So if I don't have enough, a lot of students like to do this. So they remember they don't have enough. And where am I going to take that from? Can I take it out? Oh, I got to take it out of one of these 10s. So I take it out of this 10 right here. And again, we know that 7 wants to be a 10. What does he need? He needs a 3. So again, all I've done is add 3 and 3 to get 6. I didn't have enough there, so I took away that 7 from one of the 10s. 16. Once again, you can rewind it, because I find that some adults find this to be so easy it's hard for them to understand. But children love to do mathematics this way, do subtraction this way. I've actually had students thank me for teaching them how to do this. Let's try another problem quickly. All right, and the last one we're going to do here is 34 take away 9. Again, do we have enough? We don't have enough. So again, where am I going to take that 9 away from? We're going to take it away from one of these 10s here. So again, don't have enough. And all I have to do is see that, well, what am I going to do? I'm going to just add 1. Just 1. Because a 1 will fit right there. You can see it. Oh. So 1 and 4, 5. And there's only 2 10s left. Very simple, very easily. Now, why do we do this? Well, you'll see. Let's take a real-life situation where we're making change out of 100. Now, the idea here is not to be dependent on the blocks. Once you understand the concepts, doing math is very easy. Now let's make change out of a $100 bill. Let's say I have $100 and I have an amount of, give me an amount, any amount.
$37.29.
$37.29. $37.29 is the amount. How much change do I give? Well, I'm going to build 9s and a 10. So let's do it very quickly. What does this need to be 9? 6, 2, 7, and this needs to be a 10. Done. That fast, that easy. Let's do another one, quickly. And now you know what I'm doing. Now you can see, by playing these games, building 10s, understanding that numbers are made up of other numbers, knowing that 9 can have a party, and understanding that all the blocks want to be 10s, well, now I can do math quickly and easily in my head because I understand the concept. You don't have to rely on the blocks. One of the things that happens often with teachers is they want to build every single problem using the blocks. Well, that's not the point. The point is to understand the concepts so that you can do the mathematics. So, give me another number, quick.
3764.
We just did 37. Give me another number.
64.63.
64.63. Like it. Again, what do I have to do? Build a 9. Need a 3. Need a 5. Need a 3. Need a 7. Done. It's that easy. Multiplication. Multiplication is the absolute milestone in mathematics because it allows you to count very, very quickly. So we spend quite a bit of time on the multiplication, making sure that the children understand their multiplication tables and can do them backwards and forwards. I've had many cases where children were having difficulty, or students, not just children, adult students, that were having difficulty in algebra, and spending a little time with them, I discover that they are not really confident on their multiplication tables. So multiplication is the absolute milestone in mathematics, and the way we teach it makes it very simple and very easy, and actually kind of fun, especially if we get to the children young enough. Let's take a look at this. We said that there were 5 concepts in mathematics. Well, concept number 1, all we're doing in mathematics is studying numbers. All we can do with numbers is count. That's where we're going to count very, very quickly. We only count things that are same. Highest number we're going to count to is 9. And then the third concept is we form rectangles to facilitate counting. In other words, we form rectangles to make it easy to count. So we've made a rectangle here with some 6s, 3 6s. How many in this rectangle? Well, if I have 3 6s, we have 6 taken 3 times here. Let's count it. 6, 12, 18. But if I want to count very quickly, I can just count the edge. 1, 2, 3 by 1, 2, 3, 4, 5, 6, and I know the whole thing is 18. 6 taken 3 times is the same thing as 18. And you'd be surprised, young children discover for themselves that actually 3 taken 6 times is also 18. Now, if I make a rectangle and the whole thing is 18, one side is 6, the other side must be 3. And we can see here that multiplication and division really are inverse functions. Now, can you see that 6 is contained in 18 3 times? Here they are. 1, 2, 3. I bet no one ever told you that this symbol right here is shorthand for rectangle. All right, let's get a slightly bigger problem together here using the blocks. Very simple, very easy still, but just the concept of it. 12 taken 11 times. Can you see that across here, it's 12. 1, 10, and 2 blue ones. We can call this 3 because these are different. We only count things that are same. So I have 1 of these and 2 of these. 12 across and 11 up. So I can put this way, this way. Well, what do we see here? Well, I can see very easily that I have 100, 3 10s, and 2. But if I just write it that way, Mrs. Crabtree might not be happy with that. She might say that you copied off of somebody's paper. So we need to be able to show our work. So let's show our work very quickly. All right, let's show our work then. So what we see here is I've drawn some boxes that will relate to our manipulatives. And also I'd like to interject here, usually when we're teaching with Mortensen Math, we tell stories. We tell lots and lots of stories. So these symbols over here have some meaning. And we could talk about 12 students having 11 marbles each, or something like that. How many would we have total if we had 12 students and each student had 11 marbles? Now, what I've done is I've drawn these boxes, and what I'm going to do is split and shift our manipulatives here. So here is my 100. I'm going to move it this way. I'm just going to move these guys over. And now, using your imagination, you should be able to see that I have some boxes here where each one of these is going to fit. Here, and here, here, and here. And you'll notice there's nothing here. All right, so if I'm just a very small child, all I need to do is count to fill in these boxes. Count 2 here. Count 1 blue one there. When I count down here, I have nothing. I have a symbol for nothing. That's 0, our hero. Here I have 2. And here I have 1 big red one. And now I can add them together. 1, 2, 3. I'm just counting. And we can see that 12 taken 11 times is 132. Any little child can do this kind of mathematics. Now here's a similar problem. 12 taken 13 times. Once again, very simply, all we need to do is be able to count. So 12 taken 13 times. Can I see what's going to be in each box? Well, to make it a little more clear, simply split and shift here. Now we can see what goes in each box. And I could even do this if I wanted to. Make it absolutely clear for the adults watching. You see now we have the boxes here. They're not quite as perfect, but all we have to do now is count. How many here? 6. How many here? 3. How many here? There's nothing in that box. And then just count them all together. 6, 1, 2, 3, 4, 5, and 1 big red one. 12 taken 13 times, 156. Very simple for small children. Very, very simple for even 4- and 5-year-old kids to understand. All we're doing is counting. Now, we can teach them as time goes by. 3 times 2, 3 times 10. 10 times 2, 10 times 10. Instead of just knowing or using the algorithm, multiply this, and a lot of times you'll even hear the child say 1 times 2, 1 times 1. When actually this is a 10, and this is a 10. Very simple. Now let's go back to division using a familiar set of manipulatives, the 6s we've already seen. Here we have 6 taken 3 times, and here we have 3 taken 6 times. Now, for a small child, or a student again, we can count this side, 1, 2, 3, and we can see that this side is 1, 2, 3, 4, 5, 6. 3, 6, and here I see it's 6 3s. Now you really can see that the multiplication and division are inverse functions. You can see it very clearly. Here I have a rectangle, and here I have a rectangle. The whole rectangle is 18. And on this one, we have 6 is contained in 18 3 times. Here I have 3 is contained in 18 6 times. Once again, that symbol is just shorthand for rectangle. And children can play games where they put a whole bunch of these different blocks, 4 7s, 3 5s, put them all over the board, and then they pick up the blocks and write underneath. They write the sides and what's inside. This reinforces their multiplication skills and gives them a thorough understanding of the concept of division. All right, let's take a slightly bigger problem. And in Morton Math, we always say bigger is funner. It's not good grammar, but bigger is more fun. Now, what I have here is a rectangle, and you'll see that it's built slightly differently than when we were doing multiplication. And there's a reason for this. Once again, a uniform methodology for the visualization of the mathematics. Now, again, all we're doing with mathematics is counting, right? First concept, mathematics is the study of numbers. All we do with numbers is count. Highest number we're going to count to is 9. We only count things that are same. Again, we're just using rectangles to facilitate the counting. We're not even into the concepts of 0 or 1. Now, let's see here. If I have 132 and one side is 12, you can see that this side is 12. We can count it if you're a small child. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or we can just count one of the blue ones and two of the green ones. And we have quite a few lessons about place value and so forth. But it goes very, very quickly because you'll see that it's pretty redundant. It goes pretty fast. We can see that this is 100. That's what that one means. 3 tens and 2 units. So if I have a rectangle where it's 132 and one side is 12, what must the other side be? Well, any little kid can see that this is 1 and one of the green ones. Now you remember, and that's it, we're done. But wait, it can't be that easy, and we have to show our work. But that's it. Now remember, when we were doing 18, the 6s and the 3s, we just counted the edges, 3 and 6. We didn't count the insides. Well, it's the same thing here, where we don't count these two or more here, we just count the edges. If this edge is 12, and actually you can see that this side is also 12, this side is 11, that's it. If this side is 12, this side must be 11. Now, what happens once again when you have to show your work? Well, when we show our work, all we're going to do is split it a little bit like that, so we can see the difference there. Can we see that right here we have 100 and 2 tens? 100, 2 tens. It's the same as 120 in English. What's left on here? Well, I can see there's 12 left. Now, when I count that 12, all right, we're done. It mirrors the work. Now, let's tell that story again, giving it some more meaning so that it's not just some algorithm for solving this. And what I see a lot of children do is 12 goes into 13 once. Well, it's not really 12 going into 13, is it? And doing the subtraction, or they just learn multiply, subtract, multiply, subtract. Let's learn the concept of it. Let's think about the concept of division. We're going to tell a story about Boy Scouts. All right, let's tell a quick story about Boy Scouts. There are 12 Boy Scouts, and they go and pick, I'm from Hawaii, 132 pineapples. How many would each Boy Scout get if the farmer tells them to take them home, divide them up equally and take them home? So let's get out our pineapples. Here's 100, 3 tens and 2, 132 pineapples. And now I'm actually going to get the Boy Scouts out. And here we have 3 of them. All right, here's a bunch of them over here. Look, some of them actually showed up in uniform. I don't know about you, but when I was a kid, nobody showed up in uniform. But here's 3 of them that showed up in uniform. Here's a couple of tall Boy Scouts. Here's a short Boy Scout over here. And now what we have to pass out our pineapples. Can we pass them out one at a time? Oh, that's going to take forever. We've only got an hour here. So let's see, could we pass them out 10 at a time even? 10, but then I'd have to start breaking up this one. Could pass them out like that, but then I'd have to break this one up to finish. All right, so can I pass them out really quickly? Watch this. I can think of a way to pass them out very quickly, just like that. Now, can you see that he gets 10, and this guy gets 10, and the short Boy Scout over here gets 10. Everybody gets 10. How many are left? 12. Are we done passing out pineapple? Well, we still got to pass out these 12 pineapple. Now we can see that each Boy Scout gets 11. 10 and one more. And we can see, again, that our notation mirrors our manipulatives. Where first we passed out 120 and we had 12 left. We weren't done passing out our pineapples when we had those 12 left. We pass out 12 more, and now we're done passing out pineapples. And let's take it a step further. What if I had 133 pineapples? Let's get this extra pineapple in there. Well, then you can see that instead I would have had 13 left over. And then when I passed out 12 more, I'd have 1 left. What do we call that? A remainder. It remains outside the rectangle. But this farmer says, well, you can't take any pineapple home unless everybody gets an equal share. Well, the little kids will always say, well, what are we going to do with this one pineapple? And the little kids will say, eat it, give it to the farmer, throw it away. But no, we want to divide it up equally among all those Boy Scouts. What do we need? Well, little children will tell you we need a knife. And what do we have to do? We have to take this one pineapple and cut it up into how many pieces? Well, there's 12 Boy Scouts. So of course we have to cut this pineapple into 12 pieces. Now, instead of just putting remainder 1 there, which is what the first C, we can start getting into fractions. And they can see that it's not, I've seen children do this. Because they couldn't remember which one to put it over, because they just learned some memorization technique or some algorithm to solve this, and then they got confused at the very end, and instead of putting 12 there, they put 11. But if you understand the concept of division, we understand that it's that 1 divided among those 12 Boy Scouts. Division, very simple. Let's move into fractions. All right, let's take this simple problem in fractions. 1/2 plus 1/3. Well, that should be simple, right? I've given this problem to older students, sometimes juniors and seniors, just to ascertain where they are in their mathematics. My child is having trouble with algebra. Well, let's see what happens here. Of course he's having trouble with algebra. Concept-based teaching, this will never happen. But if you just memorize some rules and algorithms and some memorization techniques for solving problems, this can often happen. What happened? Did the rules change? We're just adding fractions. The rules all changed. A lot of times students have been learning basic operations for a few years even, since kindergarten, and they've never seen a fraction. So when they come to fractions, they think, wow, the rules changed. The rules didn't change. And by the way, what we're going to show you here is just one of the methods we have for teaching fractions. And some of the pieces that we use for fractions, we use other manipulatives also to teach fractions. What if I use this? What if I use this algorithm? Which is just I use that word, it's just all that's a fancy word. All that is a fancy word for problem-solving technique. Let's see here. I'm going to multiply this one times that one, and that one times this one. And then I'm going to multiply this times that. Oh, wait a minute. Yeah, and then I'm going to add these guys together. Wait, I multiply this times that, and then I add those two together, and then I multiply these two together, and of course I come up with 5/6. Seen classroom situations where this is the way it's taught. Well, let's see, and they even have the little arrows in the textbooks. This is no help. What we have is concept number 2, where what we're going to do is count things that are same. So let's get a basic understanding of what these fractions mean. All right, what we have here are some fractions tiles. And what I want to stress is that this is only one of the ways that we can explain fractions to children. Now, do you see here I have 1 and I've made it bigger so I can manipulate it and we can talk about it. There's 1, but now here's 1 broken into 2 parts. And here's 1 broken into 3 parts. And of course we could break it into 4, 5, 6, 7, 8, 9, etc. Now, let's see. Further I can go here and see that I have actually 1 of 2. It would take 2 of these to make this. In other words, it's half of this. And here I have 1 of 3. How do I write this? Need some symbols. 1 of 2 parts. 1/2. This is the numerator. It tells me how numerous. This is the denominator. The denominator, the name of it, tells me what kind. So here I have 1 of the halves kind. Here I can show 1 of the thirds kind. And if I had 2 of them here, of course I could say I have, how numerous is it? Well, this time it's 2 of the thirds kind. So let's get back to our problem. What I had was 1/2 plus 1/3, and I wanted to know how much I had. And to make it more real and tangible to the students, let's tell a little story. The story is very simple. I have a box of cereal, actually 2 boxes of cereal. One is half full, and the other is 1/3 full. And I want to put them together. Now for little kids, we can just ask the simple question, if I put 1/3 and 1/2 together, will I have enough room in the box? Take it a step further, if there is enough room in the box, how much do I have? How full will the box be? Well, here's 1/2 and here's 1/3, and we need to understand that fractions, like you and I, don't like to wear the same clothes every day. In fact, sometimes they like to wear disguises. Now, here is 1/2 with no disguise on, but now I put a disguise on it. Here is 1/2, but now it's 2 of 4. But you see, it's still just 1/2. Now it's 3 of 6, but it's still just 1/2. Equivalent fractions. Here is 1/3. We can do the same with 1/3. 1/3 is the same thing as 2, 1, 2 of 6. 1, 2 of 1, 2, 3, 4, 5, 6. And when you get larger, you can see that we can also teach skip counting and multiplication using these fraction tiles at the same time as we're teaching fractions for the very young students. Now, let's see. Because I'm pressed for time, I'm just going to do this. I know, because I have some experience in mathematics, that I want 6th kind. We can develop that with the students. And once again, because I'm doing this very quickly in an overview, fractions alone, we could spend 2 hours teaching fractions on a tape or on a DVD. Anyway, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, we've got same kind now. We have 3 of the 6th kind. And you can even see if I flip this around that these pieces are exactly the same. They're exactly the same size. And again, this is only one of the ways we teach fractions. Here I have 2 of the 6th kind. Now that I have same kind, remember concept number 2, we only count things that are same, I can see that I have the same kind here. 3 and 2 is simply 5 of the 6th kind. And we can see that it would fit in a box. Because the box isn't full, it's 5/6 full. So that's how we get 1/3, or excuse me, 1/2 plus 1/3 is the same as 5/6. And what we did is we just multiplied by 1. And when we get to the algebra, this will be very important to understand. Right? Instead of all those arrows, we just multiplied this by 1 to get 3 of the 6th kind, and multiplied this by 1, 2 over 2 is the same as 1, to get 2 of the sixth kind. It's 5/6. We make this simple and easy for the children to understand. And this, I took a slight leap here, but all we're doing is showing clearly and concisely fractions. Now, one thing that I've had happen to me on more than one occasion is I have teachers ask me, well, how come when you multiply fractions they get smaller, and when you divide fractions they get bigger? Because it seems that in regular numbers, if you do division, numbers get smaller. And this shows a fundamental misunderstanding of what we're doing. All we're doing is counting. And in order to make these ideas clear to you, you'll have to watch another training video where we do fractions. But certainly it's not the fault of the teachers. If they've been taught this way, and the people that taught them have been taught this way, they might get confused as to why when you multiply things seem to get smaller. Nothing gets smaller, we're just counting. And when you do division, things seem to get bigger. But nothing really gets bigger, we're just counting. Here, we just started with a simple problem in addition. All right, let's move on to algebra very quickly. We need to develop some concepts in algebra. We know what the pieces are called. Here I have a 10. We played with this a little bit. And right next to it I have a bar where I don't know how many it is. There are no lines on this. You see that here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here it's just smooth because algebra is not a rough subject, it's a smooth subject. Here is 1. Maybe it's less than 1. We're not sure. Maybe it's 5. It could be more than 10. I mean, if we use our imagination, we can put lots of lines on this, and it could be 15 or 20. It could be anything. It's always varying, always changing. In mathematics, we call this a variable, and we need to name our variable. What should we name our variable? Always changing, always varying. Well, what are we going to call our variable? Let's call it x, since we don't know. Can any little child do this? Children like to do that. In fact, before they can write numbers, they can make an x. All right, so let's take our x's, and as we develop this, the children will hear that it's x, even if it's 3x or 5x or 6x, and play with them a little bit. Here, the symbol x plus another x. How many x is that? Or I can do it this way. X plus another x. How many x is that? Well, if I have an x and another x and I add them together, is it not visually obvious that all I have there is 1, 2x? In fact, here it's so clear. It's the same thing. Over here, it's the same as over here. X plus another x is just 2x. Now, many college students have a hard time here when they see, they're not college students, but high school, well, sometimes college students, I've worked with them, that where'd the 2 come from? What's going on here? What happened? I have an x and another x. 2 of them? Well, no, we don't have an x square. We have 1x and another x is just 2x. Now all I've done is add another x. So here I have 2x plus another x. How many x? How many there? Well, we can see quite clearly it's just 3x. 2x and another x, 3x. And it becomes clear what we mean when we say that the 1 there is understood. Alright, we spent a little time playing with x. Now we're going to do a 3-period lesson with all of these pieces in algebra. Normally we would spend a lot more time developing this piece right here, but because it's just a short demonstration, 1-hour introduction, we're just going to tell you that this is an x, is our friend x. Here is a unit. Now, this is also an x, and it's smooth. Well, what is this? Well, it's an x. And what shape is that? A square. So we're going to call this one x squared. And we write x squared like this. It's x two ways. It's x this way, and it's x this way. It's x by x. Here I have x, and here I just have a unit. So what I have here is 1x squared plus 1x plus 1. What if I did this? Well, now can we identify what we have? We have x squared, 3x, and 2. Now, a 3-period lesson goes very simply and very quickly. This is an x squared. This is x, or these are x's, and these are units. And I could write it down here to make my symbols match my manipulatives. Just with the blocks, this is x squared, this is x, this is 3x, and these are units. This is, now, you ask the student, show me which is the x. Show me the x squared. Show me a unit. And you can play back and forth. And then the third thing is simply, what's this? The student should be able to say, x. What's this? X squared. Now you know too. So let's take these pieces, x squared, 3x, and 2, and do a quick problem in algebra where we're going to do polynomial division. All right, what we have here is still x squared, 3x, and 2. And I'm going to give you lots of information. I want you to make me a rectangle out of x squared, 3x, and 2. And I'm going to tell you that one side is x plus 2. Can you build me a rectangle like that? Should be familiar from the Boy Scout story. Let's see here. Put these two guys like this. And I'm putting this here. And that leaves a space for the green ones. Now, can you see that I have x plus 2 across? This really is x plus 2. I couldn't call it 3 because these aren't the same kind. I only count things that are same. I know that this one's called x, and here's 2 units. There they are. In symbolic form, using the symbols. Here is x plus 1. You see that this side is just x plus 1? X plus 1. Any little child can see that. And suddenly we're doing polynomial division, and it's really just that easy. All right, can you see, to solve this problem, all we had to do is count to 3. 1, 2, 3. We never got off this hand. We never got off this hand. Algebra, polynomial division, not difficult. Any young child with the blocks can see this. And in fact, they can draw this. Because when you get those 3 sheets of paper for the GMAT or the SAT or the ACT, it says, here's 3 white sheets of paper. Good luck. Now, once we've had a 3-period lesson and we know what all the pieces are, let's apply this and just have a little fun adding some algebraic expressions. So here I'm having x squared, using the symbols, plus 3x plus 2. And here I have 2x squared plus 4x plus 4. I remember putting this on a board for a bunch of 7th graders. They went, oh, that's hard. We can't do that. Sure you can. Let's just draw them. Here's my x squared, 3x, and 2. Here's my 2x squared, 4x, and 4. And now all I've got to do is add them together. How many x squared? We'll count the big ones first. 1, 2, 3. What kind? 3x squared. Now how many? 1, 2, 3, 4, 5, 6, 7 x, because that's the kind, 7 of the x kind, 7x, and simply 6 units. Very simple, very easy once you can draw them. And some students will want to put a line here and draw it all together to match the symbols. But all we're doing is counting. All right, let's do some more algebra where we just give you a little bit of information. We want you to form a rectangle and count the sides. We call this factoring. So let's take, again, x squared, 3x, and 2, and form a rectangle. And count the sides. So I need x squared, 3x, and 2, and I need to make a rectangle out of that. Now with directed discovery, we give the children time to figure out how to make a rectangle out of these pieces all by themselves. But because we're doing a demonstration here, I'm just going to build it for you very quickly. Now we can do it either way. This way, that's division. This way, is multiplication or factoring. What I've done is put one on the side, the rest on top, and that leaves room for these two little green guys to fit in there. And once again, all I have to do is count the sides. I can see that it's x plus 1 across, and it's x plus 2 up. And all I'm saying is that x squared, 3x, and 2, this whole rectangle, these are the sides, or the factors.